So today we'll start our class. So so in the previous class we uh, mainly discussed about the van der Waals gas equation. So let me just remind it to you once again. So this was the gas equation. So now if you simplify this gas equation, it will become like this. So now if you plot this equation as a in terms of T and V, this for different temperature, the curves looks basically takes a shape like this. So for higher temperature basically, so it basically uh, attains the behavior of an ideal gas. Okay. Now from this since it's a cubical equation, so uh, there are three roots. So since there are three roots, so either three roots should be real roots, or if there are there can be two imaginary and one real. Okay. So for lower temperature case, these are the basically the three roots, and at the critical for the case of critical isotherm, there is only single real root exist. Okay, but this is the point where the critical behavior is basically located. So P, PC, VC, and this temperature is TC. Okay. Now, this curves basically shows this critical behavior and very well with experiments, but uh, in this region where this condensation happens, experimentally it has been find out that this in this condensation region, this part of this curve should be plateau, right? But here, from the theoretical expression, it shows this kind of behavior. So it's not necessarily obeying the experimental nature what we already find out. Okay. So apart from that issue, the other parts of this curve is basically well explained what we got from experiment. Now we have discussed that uh, in order to get this critical point, the conditions are basically uh, from the equation of state, we have to basically satisfy these two conditions. Okay, we have to satisfy these two conditions in order to get the critical points. Okay, so for the van der Waals gas, we have done it actually. So for the van der Waals gas, we got uh, this critical points in terms of as a constant basically, which depends upon A and B. Okay, so Vc was equal to 3b, Vc equal to A by 27 b square, and Tc equal to 8a by 27 rb. Okay, and we also define one quantity, that is this critical ratio, that known as critical ratio. This is basically just dimensionless number, which is the ratio between RTC by PCVC. So for the case of van der Waals gas, if you put all the values of this critical constant, critical parameters here, you will get this critical ratio, value of critical ratio as 8 by 3, which is roughly around 2.666. Okay, and for the case of ideal gas, it was 1. Okay, this is for van der Waals case. This is for ideal gas. And we already discussed that there are other gas law also exist to basically explain the behavior of real gases apart from this van der Waals gas equation. So there are gas equations like mm, Clausius equation, Barthelot's equation, Sahabo's equation. So there are a lot of equations are there also. So for that different gas laws, this critical ratio value will also be different. Okay. These three are the very important relation. Okay, the expression of PCVC and TC, and also you have to remember the other way. Okay, so you can also write this constant value A in terms of PCVC and TC also. Okay, so that relation is also important. You can write A also as 27 by 60 or 4 R square PC square by PC, or you can write in terms of TC and VC also, 9R by 8 TC into VC. You can write B also as VC by 3. So depending upon the problem, you have to use this different version of this relation actually, either in terms of TC PC or TC VC or PC VC. Okay. Next, we discussed about the virial expansion of this van der Waals gas equation. Okay. So this that is basically you can basically do the virial expansion in terms of volume. Okay, so this was the equation, E plus A by V square, V minus B equal to RT. You can write it like this, PV equal to RT 1 by B by V inverse A by V. Now from here you can basically expand this thing in terms as a series, right? So as an infinite series. So from there you can write this equation like this, RT B by A by V plus RT B square V square. There are also higher order terms, okay, which becomes basically uh, so when you basically approximate the behavior of this real gas, so you can basically neglect the higher order terms, okay. So you can take up to the second order or maximum up to the third order, okay. These are the basically the this virial coefficient. So first is alpha, that is RT, beta is RT, B minus A, gamma is RT, B square. So these are the different orders of virial coefficients. Okay. Now we'll also discuss about Boyle's temperature, where basically the temperature where real gas started behaving as ideal gas. So that means the self we will neglect the terms from the after the second order terms, and then the equation will become like this. Now from here, if you want to make this gas to behave like ideal gas, so we have to make this term also equal to 0, right? So if you do that, you can write temperature as equal to T by R T, right? So R T. So this temperature is known as the Boyle's temperature. Okay. Next, we have also discussed about the zeroth law of thermodynamics. So zeroth law of thermodynamics, what basically it states is that law. So what it basically states is that if A is thermally equilibrium, A is in thermal like equilibrium with, let's suppose, C, and C is also in thermal equilibrium with B, then A and B will also be thermally equilibrium with each other. Okay. So to basically quantify whether this A, C, or C, B, or A, B, uh, like whether they are thermally are in thermal equilibrium with each other. So to quantify that, we need a thermodynamic quantity. Okay, and that thermodynamic quantity we defined it as temperature. Okay, so, so same temperature basically gives us the systems of thermal equilibrium. Okay. So this concept of temperature basically comes from this concept of thermal equilibrium. Okay. Now, so from there we have defined different temperature scales, right? So to measure those temperature scales, to measure like the temperature in different temperature scales, so we need different thermometric quantities. Okay, so this thermometric quantity means this quantity basically depends upon the temperature of the system. Okay, and also it needs to change linearly with the temperature. Okay, so if we define, so let's just write it x as a thermometric quantity. So it should vary linearly with the temperature. So x a function of theta. Theta is temperature here. A theta plus b. Okay. Now since there are two basically constants are there. One is this A and one is this B. X can be any thermometric quantity that we have discussed. It can be pressure, it can be volume, it can be length. Okay, since all of these things will vary with temperature, so you can take it as thermometric property. Sorry, it varies with temperature, so you can take it with as a thermometric quantity. And in order to calculate these two constant A and B, we have to calculate x at ice point, that is at 0 degree centigrade, and at steam point. Okay, that is at 100 degree centigrade. So if we calculate this thermometric quantity at these two temperatures, so we'll get basically two equations, right? And we have two variables, two parameters, right? So from solving these two equations, we'll be getting this value of this parameter a and b, right? So let's denote x at 0 degree at x naught and x at 100 degree as s100. So now we can write T as x0 and T as x100 minus x0 by 100. By solving this equation, basically we'll get this. And if you substitute these two things, in this original equation, we'll be getting theta x as, so theta will goes to the left hand side. Okay, so theta will become a function of x. So theta x, it will be x theta minus x0 by x100 by x0 into 100. As you can see, so x0, x100 and x0, these are some fixed quantities, right? Now by just measuring what is the value of x at that particular temperature theta that you are interested in, from that value you can basically calculate the exact value of this temperature using this law, provided that the x should varies linearly with the temperature. Okay. Okay. Yeah. Okay. So these are the some of the things that I've discussed in the last class. So now in today's class, we'll be mostly discuss about the properties of thermodynamics and how these properties, like these macroscopic properties, are related with each other. Okay, for different cases. Okay, and you also discuss some of the standard uh, uh, what is this called, standard names or terms that we used in thermodynamics. Okay, so in thermodynamics, basically we deal with macroscopic quantities. Okay, so how these macroscopic quantities are related with the energy of the system. Okay, so there are like macroscopic quantities means how like systems like collectively behave. Okay, so like pressure. Okay, for a gas system, thermodynamic quantities are like pressure, volume, temperature. Okay, these are the microscopic quantities. Okay, how this quantities basically behaves. Okay, that thing we will observe in thermodynamics. Okay, so for a gas system, these are some of the important this macroscopy, not macroscopic. Okay, these are some macroscopic quantities. Similarly, if you consider, let's suppose a paramagnetic material. Okay, so like paramagnetic material means is made in the material. The atoms are like this magnetized atom. Okay, so the atoms have spin and all. Okay, so they can align with each other when you apply some external field also. Okay, so for this kind of a material, the thermodynamic properties maybe will be the net magnetization, the susceptibility, the specific heat and all. Okay, so there are we in this course we'll be mainly talking about the gas system, but these are also some different systems where you can also calculate this macroscopic properties. Okay, next there may be stretched wire. So for a stretched wire, this is also thermodynamic system. Okay, for a stretched wire, different macroscopic quantities are like the tension. The tension, they write it as capital gamma. Okay, uh, the length, the temperature, these are some of the macroscopic quantities for a stretched wire. Okay, so basically how this macroscopic quantity behaves, that we will learn in the course of this thermodynamics. Okay. Now for so there are two types of parameters, or you can see this macroscopic quantities are there. So uh, first is the intensive parameters or quantities. Okay. Now intensive parameter means the parameter that doesn't depends upon the mass of the system. Okay. So the parameters like pressure, temperature, tension. Okay, these are the some of the quantities. So that means like if there is in a container, if there is certain number of gases there, okay, with a particular temperature, let's suppose T. So if you remove some gas from this particular container, the temperature will not change simply, right? Temperature will remain fixed. Similarly, for the case of pressure also, okay. If you remove some gas, the pressure will not change. So this doesn't depends upon the mass of the system. Okay. So that's why it's known as the intensive properties or intensive parameters. Next is the extensive one, which is opposite to the intensive parameter. So it depends on mass of the system. So this includes volume, mole, magnetic moment for the case of this paramagnetic materials. Okay. Or if a system that have some magnetic poles that is associated with the atoms, in that kind of system you can consider magnetic moment as an extensive parameter. So here uh, so from the definition itself you can easily relate, right? So let's suppose there is a gas with a certain amount of volume V, right? If you remove some gas, if you remove half of the gas from here, so the volume will become V by 2, right? So certainly it depends upon the mass of the system. Okay, so that's why it is known as the extensive parameters. Okay, yeah. So these are the two types of variable, two types of parameters. Yeah, you can ask any question.
Is it always a linear dependence or can it be any dependence, any type of dependence?
Yeah, it can be any type of dependence. Okay, for the case of volume, it can be linear. Okay, but it for other things like magnetic moment and all, it can depend in a different way also, non-linear way also. Okay,
Okay, okay.
yeah. Okay. Now, uh, so so thermodynamic equilibrium. Okay, see, this is a very important concept. So, okay. So a system. Let's suppose so there are two type of nomenclature you will be facing. One is called system, and one is called the surroundings. Okay. So what? So system means the thing. The system is the thing that we are interested in, that we are interested to study. Okay, that is our point of interest basically. And surrounding means the rest of the universe. Okay, the rest of the universe. Okay. Now, so the system is in thermal equilibrium with the surroundings. Okay. So how to define that? That the system is thermodynamic, not thermal, thermodynamic equilibrium with the surroundings. To measure this thing, what we have to calculate is that one is called the thermal equilibrium, right? So three things needs to be in equilibrium in order to quantify, in order to verify whether the system is in thermodynamic equilibrium or not. Okay. So the first thing is the thermal equilibrium. Next is the so for, in order to basically quantify whether it's thermal equilibrium or not, we have to calculate the temperature, right? We have already discussed previously. So temperature of the system should be equal to the temperature of the surroundings. Okay. Similarly, second thing is the mechanical equilibrium. Okay. Mechanical equilibrium, if there is not any unbalanced force between the systems, right? So if there are no unbalanced force in that case, in general, it is basically quantified by the pressure actually. Because the pressure of the system is equal to the pressure of surroundings. In that case, we may quantify it as like like mechanical equilibrium with the surroundings. Okay. And third is the chemical equilibrium. Okay. Chemical equilibrium means if there is no particle that is exchanging between the surrounding and the system. Okay, so like there is basically not any exchange of mass that is happening into the system. Okay, so delta n exchange should be equal to zero in order to qualify the system as chemical equilibrium. So if the system obeys all of these three types of equilibrium with the surroundings, then you can basically say the system is in thermodynamic equilibrium with the surroundings. So now next there are basically four types of systems. So in the problem, these names are basically important when you solve the problems, because in the problems they mention different types of system. Okay, so one types of system is this different different system. Okay, so from the name itself you have to basically uh, know how what is the type of the system. Okay, so first is the open system. Okay, open system means uh, the system can exchange particle. Okay, exchange particle or mass. Okay, second is the closed system. Closed system means system does not allow mass exchange. Okay, third is the insulated system. Insulated or isolated. Okay, isolated system means basically there is no exchange of heat with the surroundings. Okay, no exchange of heat. And fourth one is the diathermic system. Okay, diathermic means the system can exchange heat with surroundings. Okay, these are in general four types of systems are there. Okay, and this is the insulated system. Okay, so there is also definition, I guess, that is the isolated system. Okay, I don't know whether they are equal or not. So isolated are like completely isolated systems. Okay, so they cannot allow to exchange both heat and also the particles. Okay, no heat and no mass. Okay, this is known as the isolated system. Okay. Yeah. So basically, the main point is that, see, if in the problem it is mentioned that there is some closed system, so closed system means the system can allow doesn't allow mass exchange, but it can exchange heat. Okay, that is the main point. The meaning of closed system. Okay, but in the problem it's mentioned that if the system is isolated, so that means cannot allow to change both the mass and as well as the heat. Okay, this is the difference. Okay. Closed system means it can only doesn't allow only the mass, not the heat. Okay. Okay. Yeah. And also there are two other processes. Okay. So the problem also it is very important. This names. So thermodynamic processes. One is the irreversible process. Okay. Irreversible process basically uh, any kind of real life processes. Okay. So you cannot basically reverse it. Okay. Uh, so this the reason behind the existence of this irreversible process is that there are dissipative forces. Okay, so that because of this dissipative forces, when you do some kind of work and some kind of work into the system, these dissipative forces basically consume some energy that you cannot basically get back when you reverse the work. Okay, so because of that, the system cannot basically revert back to its original state. Okay, that's why it's known as the irreversible process. Okay, so in real life, whatever work you do basically, that basically involves some dissipative forces, right? So basically, like if you press a piston inside a container, so that piston faces some frictional force, right? So that frictional force basically act as a dissipative force, which basically drain it energy. So basically, by reversing that whole process, you cannot basically bring back the system to its original form, right? So that's why, like any kind of real life system is basically any kind of real life phenomena that is happening basically obeys this irreversible process. Okay, so this basically includes uh, dissipative forces. Okay, so which means reversing the system does not put both the system plus surroundings. Okay, system plus surroundings to the original state. Okay, and this is the next is the opposite of this. So this is a reversible process. So this is basically completely a hypothetical concept. Okay, reversible process. In general, to make any system reversible, completely reversible, 100% is not possible. Okay, because in that case you have to make the system completely ideal. Okay, ideal behavior, but no system in universe follow this ideal behavior, right? So so this is opposite. Okay, so no dissipative forces exist. So system plus surroundings moves back to original state. If you basically reverse the process, okay, this is the reversible process. Okay, so the example is like this. So let's suppose you have an ideal gas. Okay, let's suppose so this is, let's suppose, a PV diagram of ideal gas. So you took a ideal gas in a container and you basically press the container using a piston. Okay, so in this container there is this ideal gas. So let's suppose at state 1, initial state, this gas has some pressure volume. Let's suppose PV, okay, P1 and V1. So in this state diagram, okay, you can basically you can basically point the state of this thermodynamic system with a point P1 and V1, right? P1 and V1. Now, if you press the piston, right, the pressure will increase, right? So let's just point it here, okay? V1 to V1. If you press the piston, now the pressure will increase and the volume will decrease, right? So now the goes back to some kind of this kind of state. Okay. Let's now the pressure is P2 and volume is V2, right? Now in this case, since this is an ideal gas, so the pressure and volume will obey this law like PV kT, right? So this is like P equal to K. So temperature is fixed. So P basically will be 1 by V, right? Pressure and volume like changes like this, right? So if you relate P1 V1 to P2 V2, it will show this kind of hyperbolic kind of curve because this is a equation of hyperbola, right? Sorry, parabola, right? Yeah. Yeah. So this is basically related by PV equal to some constant, right? Okay. So this is the case of ideal. Okay, if the system is like ideal gas. Okay. Now, in originally, this is not ideal, okay, because this piston has some friction. So when you press the piston, there is some friction that is working between the piston and the wall of this gas container, which act as a dissipative force, right? And because of that, this curve doesn't looks like this. It will move. It will take some other kind of shape, right? Like this kind of a different kind of. You have to experimentally measure. Okay. So that is the real case, which is not ideal. Okay, so you cannot basically reverse it. Okay, so if it behaves like ideal kind of, you can easily reverse it. Okay, but if it's non-ideal, then you cannot simply reverse the process. Okay, so next there is a also concept of quasi-static process. Okay, so this is a quasi-static. Okay, the quasi-static process is basically an infinitesimal process, uh, which is basically a small displacement into the of the state, different state. It can be pressure, it can be volume. It should be slow enough to maintain that thermodynamic equilibrium at all intermediate steps. Okay, so let's suppose you change the pressure P1 to P2. Okay, let's take the change as delta P. Okay. So delta P is the called the quasi-static change. Okay, this whole process is known as quasi-static process, and this is the quasi-static change. It is a very infinitesimal process. Okay, process which basically the property of this infinitesimal process is like that it maintain thermodynamic equilibrium at all intermediate. Okay. Okay, so this is like so P1. So if P1 is in thermodynamic equilibrium, if you change, so if you do any change delta P, that is a quasi-static process. So in that case, the P2 will also be in thermodynamic equilibrium. Okay. This is a also concept. So this concept is for like to do all the calculations. Okay, so like uh, it's kind of like in when you deal with the equations of state and all, you basically change the, let's suppose, the pressure with some infinitesimal amount P plus delta P. Okay, so this dP is basically the quasi-static process. Okay, so uh, so this basically ensures that the system will remain thermodynamic equilibrium, although you have done some change delta P, but still the system remains in thermodynamic equilibrium, right? So that means like the original equation of state that is relevant for the case of P, that should also be relevant for the P plus delta P, right? So to ensure that we are considering this dP as quasi-static change or quasi-static process. Okay, so this is completely we are defining this thing to do all the mathematics and all. Okay, this quasi-static process. Okay, this infinitesimal changes because in the equation, each of the equation and derivative, what you have to do is you have to do some changes like small infinitesimal number of changes into the equation of state, right? In order to derive any quantity like specific heat and all. So that infinitesimal change, you are telling that as a quasi-static change, so that it doesn't basically changes the whole thermodynamic equilibrium of the system. Okay. So that is the significance of this quasi-static process or quasi-static change. Okay, infinitesimal change. Next, so now, okay, so these are the three kinds of processes. So reversible, irreversible, and quasi-static process. Okay. Now, so okay. Now there are certain different kinds of processes are also there, uh, which keep some of the thermodynamic constant fixed and some of the thermodynamic constants are as variable. So this is very important in the perspective of the problems. Okay, so in the problem itself, they only mention a specific type of processes are happening. So depending upon that name, you have to basically figure out which are the quantities, macroscopic quantities that remained as constant and which are the quantities that is basically varying. Okay. So first is called the isothermal process. Okay. So from the name itself, you can basically process what kind of process is that. So temperature is constant. Okay. Since it's isothermal, so the temperature or there is no basically changes of thermal energy. So this the temperature is constant here. Okay, so T is constant. In that case, uh, yeah. So in that case, the equation looks like this: PV equal to constant. Okay, for the case of an ideal gas, okay. PV equal to KT. K is already a constant and T is also a constant. So together they forms a constant, right? So PV equal to constant. This is the isothermal. Okay. Next is the Adiabatic. Okay, so this is different from isothermal. Okay, so adiabatic means no heat exchange. So in that case, for an ideal gas, this process, the pressure and volume basically related by this relation. Okay, for the adiabatic process. So if in the problem, if it is mentioned that the process is adiabatic, then you have to basically use this form of relation between the pressure and volume. Okay, uh, so for ideal gas, for an adiabatic process, the relation of pressure volume looks like this: P V gamma to the power gamma equal to constant. Okay. And this gamma is nothing is gamma, actually this gamma we have already study about the definition of this gamma. This gamma is known as the adiabatic coefficient. Okay, this gamma is basically Cp by Cv. Okay, the ratio between Cp and Cv, specific it at constant pressure and specific it at constant volume. And there is another process. So if gamma is greater than 1, in that case this kind of process has a name that is known as the polyotrop polyotropic process. Okay, or polyotrop. Okay, polyotropic process in general if gamma is greater than 1. Okay, and the isothermal, and for the case of isothermal and adiabatic process, how this basically this PV diagram looks like. So PV for isothermal looks like this, and for adiabatic it looks like this. The difference is that the slope of this curve is a bit steeper in the case of adiabatic. Okay, so is isothermal, this is adiabatic. Okay, so in the problem itself, it should be mentioned. Okay, so by looking it, it is not able to basically quantify whether it's isothermal or adiabatic. So in that case, it would be mentioned in the problem. If the problem is given in terms of PV diagrams, in that case, it should be mentioned whether it's a diabetic, isothermal or a diabetic process. Okay. Next is the isochoric process. Okay, isochoric process. For isochoric process means here the pressure is change of pressure is basically remain uh, zero. So change of pressure, so delta E is zero. So that means constant pressure of P is constant. So in that case, the PV diagram looks like this. Only the volume will change, right? Pressure will remain as constant. So it will looks like this. So uh, sorry, it's yeah, it's not isochoric actually, it's isobaric. Sorry, so it should be isobaric. Bar is the unit of pressure. So from that itself you have to remember. So it's isobaric process. Isochoric is the one where the volume remains constant. Okay. So here it would looks like this here. Pressure is remain as constant. Let's suppose at P1. Only the volume is changing. P1, P1 to P1, P2. Okay. And the seventh one is the isochoric. Here the volume is remained as fixed. Delta V is equal to 0. So constant volume. Okay, so now here, so in that case, you already know how it looks like in the PV diagram. So it looks like this. So at a constant volume V1, the pressure changes from P1 V1 to P2 V1. Okay. So these are the four types of, in general, these are the basic four types of process. Uh, According to the problem, you have to basically figure out what types of process they are mentioning. Okay, what are the properties that remain fixed? What are the properties that will change? Okay. Next is the work done. Okay, so work done is basically so if you fixed one quantity and you changed another quantity, so in that case the system will do some work. Okay, so basically there is some physical displacement that is happening into the into that particular quantity, microscopic quantity of the system. So because of the physical displacement, the system, both the system and the surrounding will do some work. Okay, so that work will be different for different types of processes. Okay, that we will discuss. So work. This because of macroscopic forces that cause physical displacement. Okay. Displacement means displacement in terms of macroscopic quantities like pressure, volume. Sorry, that is basically extensive quantities. Okay, like volume or this magnetizations, mole, all these things. Okay, so the definition is same. Delta W equal to Y into dx. Here, Y is the intensive and X is the extensive. Now, there is a very important thing regarding the sign of the work done. Okay, so if the work done is negative, sorry, positive, in that case, work done, work done by the system. Okay, system is doing some work on the surroundings. Okay, and if the work done sign is negative, so that means work done on the system. Okay, so you have to be very careful about the sign of this work done. Okay, if it's negative, then the work is done on the system. If it's positive, then work done by the system. Okay. In general, if you take pressure as an intensive variable and volume as extensive variable for a case of gas system. Okay, in general, for a gas system, we take pressure as intensive and volume as extensive. Okay, for different types of system, these parameters, these intensive extensive parameters will have, we can take different kind of different types of extensive and intensive parameters. But for gas assembly, generally we take delta W, Y as P, and X as dx as dV. Okay, PdV. Okay. So this is the expression of work done. Okay. Now we'll get back. We'll see this work done for different types of processes. Okay, like for case of isothermal, for case of uh, 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 adiabatic, isocodic, isobaric. We'll see. But before that, we have to also discuss about this first law of thermodynamics, right? So first law of thermodynamics that is related with basically the internal energy of the system. Okay. So how this internal energy of a system comes? So in a gas, there are two types of energy, right? One is its kinetic energy, right? So if the gas basically moves, it has some velocity that is directly related to the temperature of the system that we know. Velocity is related some relation with kBt by m, right? So it's basically directly related to the temperature of the system. So, so that velocity gives the kinetic energy, right? So kinetic energy so comes from temperature. Okay. And another is the potential energy. Okay. Potential energy means the gas. This gas, both of the gas particles have some potential, right? It can be so there are many kinds of potential like van der Waals potential, some interaction potential, something like that. So because of that potential, so when two gas interact, so there should be some potential energy that will be acting between this pair of the gas molecule. Okay. So these basically gives rise the potential energy of the system. So interacting gas molecules. Okay. So these two kinetic and potential energy basically gives the the internal energy of the system. That is the total energy. Okay. Okay. Yeah. So this gives the internal energy of the system. Now, this internal change in internal energy. So if let's suppose u is the value of internal energy. Now, this change in internal energy basically is related with both the change in the heat transferred into the system and change in the work done into the system. And that changes are basically related by this relation. Change in internal energy, if we denote it is a delta U, okay, delta U. The delta U basically related with the change in heat that is denoted by dQ minus the change in work done that is by delta U, delta W. Okay, for an so this is for the case of a closed system. Okay, this relation. Okay, if you consider a open system, so that means the particle can also exchange with the surroundings. In that case, there will also be a third term that is mu into dN. Okay, so mu is basically the chemical potential of the system, and dN is the particle exchange. Okay. Now for this case, and for the rest of the discussion, they have only considered for closed system. Okay, so for closed system, this is for the open system. For closed system, du is delta U is delta U Q minus delta W. So this is also known as the first law of thermodynamics. Okay. This relation is very important relation here. Okay. Now we will see different types of work done. Okay. Uh, so let's take the PV diagrams. Okay. So for the case of let's suppose a isochoric process. Okay, where the volume is basically remains as fixed. So it's V1 and pressure is changing from P1 V1 to P2 V1. Okay. In this case, as you can see, uh, for isochoric, okay, we know it's the relation is basically given by PdV, right? So here the volume. So if you do the integration, it basically gives us P delta V, right? Now here as you can see the volume is not changing. V1 is remain fixed both at the state 1 and state 2. So in that case, the work done is V1 minus V1, so it would be 0. Now, for this is for isophoric. Now, for isobaric case, let's suppose it start from here to here, right? This is let's suppose state 3. So P1 V1 to P1 V2. Okay, so in that case, for isobaric, so here you can see the volume is changing, right? So it would be P dV. So P1 to V2 minus V1. So this is these are certain expressions. So you have to just substitute the values of volume 2 and volume 1, and from there you will get the expression of the value of the work done. Okay. The next one is the isothermal process. Okay, so for the isothermal process, it looks like this. Now in this case, since it's isothermal, we know for ideal gas, PV equal to nRT, right? So, so since temperature is fixed, and let's suppose the gas is 1 mole, n equal to 1. So PV equal to some constant, right? Let's tell it as C. Okay. Now from the gas, the work done expression, you know, PdV. So now what we can do here, we can write P as a function of volume, right? So nRT, or just RT, n is 1 RT by V. So if you substitute it here, so it will become RT dV by V. So it will become RT ln V2 by V1. Okay. V1. Yeah. So this is the work done for the case of isothermal process. So isothermal is RT ln V2 by V1. Okay. So whenever you see there is some what is this called? There is some isothermal process happening from the state diagram or from the PV diagram. You can easily calculate from the information of the volume only you can calculate what is the work done that is happening into the system. Okay. Now lastly the case for the case of an adiabatic process, or for a, if gamma is greater than 1, in that case for a polyotropic process you can say, in that case the PV diagram looks a bit similar. There is a, although there is some change, there is a change, like it's more steeper than the case of isothermal process. This is the adiabatic process. Okay. Process, this is P1 V1 to P2 V2, change is like this, let's suppose. Okay. Yeah. Now in that case, the work done we know. So in this case we know the equation for this adiabatic process. It follows this kind of relation: PV to the power n equal to some constant K, or C, let's suppose. Now now similar we can write P equal to some C by Vn. The work done expression is equal to PdV. You substitute it here, W will become C by V to the power n dV. Now if you further simplify it, you can write W as P2 V2 minus P1 V1 by 1 minus n. Okay. N, given that n should be greater than 1, right? In that case only you can use this process, right? So Or also there is another way of write this work done, that is like this. Uh, let's write mu. So mu is here the mole. Okay, mu r n minus 1 by t2 minus uh, sorry, I have written it wrong. So we started from P1 V1 to P2 V2. So in that case, P1 V1 is the initial step. Okay, so P1 V1 initial. So initial state should be first P1 V1 minus P2 V2. Okay, yeah, V1 to V2. Okay, yeah, now it's fine. Here it should be initial minus final. Okay, so initial is T1 minus T2. Okay, so this is the form of work done in the case of an adiabatic process. So these formulas you have to remember actually, or you can derive it also if you forget somehow. Anyway, so these are like W. Okay, so these are some necessary formulas. Okay, so this is for isobaric, this is for isocoric, it's zero. This is for isothermal, and this is for adiabatic. Okay. In general, so basically, if there is some kind of a cyclic process is given, or any kind of process, not in general, not a cyclic process. Okay. If let's suppose this kind of process is given, okay, from let's suppose point A, or like let's suppose this is the process, point A to point B. Okay. Now from from the perspective of geometry also you can calculate. You just have to calculate. Let's suppose this is a PV diagram. In the PV diagram, from the PV diagram, if you want to calculate what is the work done here, in the geometry perspective also you can calculate from this diagram, that you can do just by calculating the area under this curve actually. Okay, if you can calculate this area under this curve, from that information also you can calculate what is the work done into the system. Okay, you know these coordinates, right? P1 V1 to V2 V2. So there are basically, so from these coordinates, this coordinate should be here. So it should be 0 V1. It's here. It should be 0 V2, right? Here the pressure is 0. Yeah. So from this, there, if you know these four coordinates, so from that itself you can basically calculate what is the region that is coming under this curve, right? From that information is basically is the work done by the system also. Okay. And this is also a way from using geometry you can calculate the work done. Okay. Now, okay. Now, next thing is the specific heat. Okay, sorry, heat capacity. Okay, so yeah, so from using this law, this first law of thermodynamics, you can basically rewrite this expression of specific heat for different types of process. Okay, now let me write it. So heat capacity. Okay. So let's first write the law. So du equal to dq minus dw, right? Now from here you can write it also like this: dq equal to du plus dw. You can write dw as pdv also, right? So du plus pdv. Okay. Now from here, what you can do, you first will write for the specific heat for isochoric process. Okay, so isochoric process, isochoric process, the volume is constant, so the specific heat or heat capacity, that should be also for constant volume, that we know. that basically represented as CV, we know, right? CV, CV, specific heat at constant volume, right? The CV expression we know, dq by dt at constant volume, right? Now, so now from here, if you see, since dv is constant, so dv is basically 0, so you can write this thing as dq equal to du, right? If you substitute this thing here, so you can get for the case of isochoric process, okay, let me call it isochoric process, the CV we can write as du by dt also. Okay, so instead of derivative of heat, we can take the derivative of internal energy with respect to temperature, and from that also we can calculate the specific heat. Okay. Next is specific heat at constant pressure. So that is for that it's known as isobaric process, right? So the isobaric process, yeah. So for isobaric process, it is known as CP, right? So CP is basically dq by dt at constant pressure. So in this case, dq expression, this is given by this. If you substitute this thing here, it will become du by dt at constant pressure plus p into dv by dt at constant pressure. Okay, so dv by dt. So this is the expression of Cp, and this is the expression of Cv for different process. One is isochoric, another one is isobaric. Okay. Now you can also write the difference Cp minus Cv, Cp minus Cv. Okay. So Cp minus Cv uh, looks like this. P into P plus du dv at constant temperature by dv dt at constant pressure. Okay. So this is a very important relation that you have to remember. Okay. This particular form of expression. Okay. Now for the case of ideal gas, PV equal to RT, if you consider du dv equal to 0 at constant temperature, in that case, this Cp minus Cv will take equal to R. Okay. Now for different this dV by dP thing, for different gas equation, it takes different form, right? That you can basically from that particular equation of state, for different gas equation of state, this dv by dp will take different form, right? So this difference between Cp minus Cv will also take different form. So that's why Cp minus Cv equal to R is very specific for ideal gas only. Okay. Different gas equation, this relation will take different forms. So these all of this discussion that we are doing right now is very general. Okay, so it not basically limited to a particular type of gas, ideal or something like that. It's a very general discussion that can be applied to any kind of system, provided the condition that the system should be in thermodynamic equilibrium. Okay. If the system is in thermodynamic equilibrium, all this relation you can basically apply to that particular system. Okay. Now you can also calculate this from the first first law of thermodynamics. You can also calculate this change of heat delta Q. So so previously we have discussed how you can change the delta W, right? Now if you know delta W, from that information also you can also calculate what is the change of heat, that is delta Q. Okay. So delta Q you already know is related with delta U plus delta W, right? So delta W we have discussed how to calculate, right? So delta Q is, and delta U is nothing but CVDT. Okay, change in heat basically. At a specific, if you know the specific at constant volume, from that itself you can calculate from this relation basically. You can calculate, sorry, from this relation actually you can calculate the change in this internal energy du equal to CVDT. Okay, so just put it here, CVDT, CVDT, and dW already know, PdV. Okay, now for different process, this change, this dq will take different expression, right? Let's take for case of you know, for let's take isochoric process. So isochoric process, this part will be zero, right? So so CVDT, so there will be only delta Q will be only depend upon the change in temperature. Okay, T final minus T initial. This is for isochoric, and for isobaric it will take delta Q will be depend on CV TF minus TI plus P into VF minus VI. Now we already know PV equal to RT. You can use this relation here. So from that relation also you can write it like this also. Using that relation you can write this expression in terms of temperature also, right? So RTF minus RTI, right? This is for isobaric delta Q. Similarly, for the case of adiabatic, okay, for the adiabatic process, this for the adiabatic process, we know CV is similar, TF minus T initial, and for the work done part, we know the relation is PI by VI minus EF by VF divided by N minus 1. Okay, N should not be equal to 1. Okay, this is for the case of adiabatic. And for the isothermal case, we know since it's isothermal, so temperature final initial will be same. So du part would become 0. So the only contribution comes from the dw part. So that we know we have calculated is RT ln Vf by Vi. Okay, this is for isothermal. Okay, these are the some expression of change in heat. Okay, dq. Okay. Okay, so these are the some useful expressions that you have to remember. There are also other thermodynamic quantities also there for the case of gas, like this volume expansibility alpha, that is 1 by V dV by dt at constant pressure. Isothermal compressibility, that denoted as beta basically, or kappa. Isothermal, so 1 minus 1 by V del V by del P at constant temperature. So this is isothermal. Isothermal elasticity, that denoted by 1 by beta, okay, or Et minus V del P by del V at constant temperature. Okay, these are also some important thermodynamic quantities that it's better to remember the expression in this differential format. Okay, because you may like for a particular gas equation you may have been asked to calculate its thermodynamic compressibility or all, or the volume expansibility. So in that case, you have to use basically this relation. Okay, you have to derivative that equation of state with respect to the temperature in order to get the expression of alpha, beta, 1 by beta and all. Okay. Okay. Next, now we'll move to the problems. Okay. So problem number one. One gram mole of ideal gas expands isothermally to 4 times its initial volume. It's at 25 degrees centigrade. Calculate the quantity of heat which is extracted for the work. Okay. The options are: option A, 1 1.5 kilojoule; option B, 5.23 kilojoule; option C, 4.78 kilojoule; option D, 3.43 kilojoule. Okay. Now, okay, so now so how to do it? So work done expression is simply no answer. Work done is integration, sorry, integration PdV, P initial to be final. So P, so this is like here the volume is changing isothermally. Okay. So since it's an isothermal process, we know the expression, right? So what is that? So this one, this RT ln V2 by V1, right? So it would be RT ln V final by V initial. Okay. So gas expands. So 4 times from the initial volume. So VF would be 4 into VI, right? So RT of ln 4. So R we know is 8.31 joule Kelvin inverse mole inverse. So if you substitute that 8.314 into temperature is given 25 degrees, so you have to convert it in Kelvin, which makes it 298 into ln of 4. In calculator, if you do that, it will gives you 3.43 kilojoule. Okay. So this is a simple problem numerical. Just isothermal. So you know it's isothermal. So you already know what is the form of the work done that is needed here. So that form of work done we have substituted here, and from that definition we can calculate the work done. Okay, easily. Okay, so the correct answer is 3.43. The next problem is, so there's a PV diagram involved here. Okay, so one, so let's write this. 1 mole of monoatomic ideal gas is taken from point A to another point B along the path ACB that is shown in the picture. So I'll draw the picture. The initial temperature at A is T0 Kelvin. Okay. The initial temperature is mentioned, that is in T0 Kelvin. Calculate the heat absorbed absorbed by the gas in the process. Okay. So let me first draw the diagram. Okay, it's very important. So diagram looks like this. So this is y-axis. This is v-axis. So initially the gas was in point A. So this is point A. Okay. So from here it takes this path. So first it moves to point C, then it moves to point V. Okay. So initially the pressure and volume is this initial coordinate has pressure and volume P0 and V0. That means this is P0 and this is V0, right? Now from here it moves to another point C, that is 2V0. Okay, twice the initial volume. And in this part also we know that at the initial point also the temperature is T0. That is also mentioned here. Okay, so that means whatever the answer is, we have to write in terms of P0, V0, T0. Okay. Next, at the point B, this pressure is basically expand to 2P0. Okay. So this point B, the coordinates are basically 2P0, 2P0. In the point C, the coordinates are P0, 2P0. Okay. Now throughout this process, you have to calculate what is the heat absorbed. Okay. The options are option A. Let me write it here. Option A is 2.5 P0 V0. Option B is five. Option B is 5.5 P0 V0. Option C is 4.5 P0 V0. Option D is 2 P0 V0. Okay. So now here, okay, so we know that during this whole process, from the first law of thermodynamics, we know dq equal to du plus dw, right? We have to calculate this dq thing, that is the heat absorbed. Okay. So in order to calculate this dq, you have to calculate both this du and dw. Okay, so du, we know the formula is cv dt, or for dw, the formula is pdv. Okay. Uh, Now we know that we have already shown you, like for some of the cases, for the case of isochoric, like here you can see isochoric, isobaric, adiabatic, isothermal. We know how this expression of delta Q looks like. We will use that actually for our benefit here. So first is the work done for the case of also one thing that is needed, that is the CV. What is the value of CV? So this monoatomic thing is mentioned. Okay, so as it's a monoatomic ideal gas, we know CV is basically 3 by 2R, right? For the case of a monoatomic gas, the values of specific that we have discussed in the first or second class maybe. So this is the value of CV. Now for diatomic it was 5 by 2, something like that. So for monoatomic it's 3 by 2. Now from the degrees of freedom and all, we have calculated it. So so for this case, so for the first case, so it would be for from A to C, right? So from A to C, we know it's only the volume is changing. Yeah, so it would be, so we know the volume changing, so it would be isobaric process. Okay, so isobaric process, so that means you have to use this one, this formula. So uh, So dq1 delta, sorry, delta q1 would be cv tf minus ti plus tw is t0 vf minus vi. Okay, the ti is t0, right? What is the tf? So for the case of tf we have to use the ideal gas equation. Okay, so we know pvt equal to, so pi vi ti equal to pf vf tf. Okay, so pi vi is p0 from this state to this state. Okay, so p0 v0 by t0 equal to pf was same, so p0 into 2 into v0, since the volume is changes to 2 v0 here, by tf. So from here if you calculate, tf would be 2 into t0. Okay, so now the delta q would be cv 2 t0 minus t0 plus p0 2 v0 minus v0, right? Now from here, so if you substitute the thing here, so uh, it will become 3 by 2 r into t0. So r into t0 is nothing but p0 v0, right? From the ideal gas equation, 3 by 2 into p0 v0, plus the second would become p0 plus p0 p0 plus p0 into v0. It would become 5 p0 v0 by 2. Okay, now for the next process, this is delta q1. Okay, now delta q2, this process is for only a to c. Okay, for a to c. Next process is from c to b. Now for c to b, the process is basically isochoric, right? The volume remains fixed here. Okay, this is isobaric, this is isochoric. Okay, so in that case, this dw would be 0 simply, right? The work done would, there would be no work done, right? So there would be only cv. cv is changing, so okay, yeah, so cv is changing, so tf, so this is the formula, right? What is this one, cv, the cv tf minus ti, right? The cv tf minus ti. So here also similar way. So initially the equation of state looks like this: p0 2v0 by 2t0, right, equal to 2p0 into 2v0 into tf for the, for this process c to b. Okay, this is the equation for c, this is the equation for b. Yeah, so now from here tf would be 4 into t0. Okay, so now if you just substitute it here, so cv would be 4 t0 minus t0, so that gives you 3 t0 into 3 by 2 rt. Just a second. Sorry, it would be 2t0. Yeah, 2t0. So it would be 2t0. Yeah, that's fine. Hmm. So it would become 3rt0. Okay. So the total change in heat would be delta Q, would be delta Q1 plus delta Q2. So this will give you 5 by 2. So you can write it as 3 P0 V0 also. So 5 by 2 P0 V0 plus 3 P0 V0. It would give you, if you calculate it, it will give you 5.5 P0 V0. Okay. Yeah. So the answer would be this one, option B. Okay. This is how you should handle this diagram. Okay, this PV diagram. Okay, so whether it's work done or heat absorbed or heat that is taken out from given out from the system. Okay, so in that case, you have to first figure out what kind of processes that are involved from the nature of the PV diagram, and according to it, you have to use the corresponding laws. Okay, corresponding formulas. Okay, or conditions. Okay. Now, the problem number 3 is a mass of certain fluid in a cylinder by means of a frictionless system occupies a volume 2.5 meter cube when its pressure is 1.2 into 10 to the power 5 Pascal. The fluid is then compressed reversibly under conditions in which the product of pressure and volume remains constant. Calculate the work that must done to reduce the volume. One point one meter cube. So basically, so the friction there is certain fluid in a cylinder. Okay, so its cylinder looks like this. There is a piston. So the piston is like the frictionless. So there is no dissipative force involved there. So it's a reversible process, or it's an ideal process, you can say. So it initially occupies a volume of 2.5. VI is 2.5 meter cube. Okay. Okay, so now what is mentioned is that its pressure is initial. The pressure is also 1.2 into 10 to the power 5 Pascal. Okay. Now the fluid is then compressed, so it is then compressed, the piston, in which the product of pressure and volume remains constant. So PV is constant. So PV is equal to some constant K. So that means it's a isothermal process, right? Since the temperature is also fixed, so to maintain the pressure and volume is equal to some constant. Calculate the work done that is needed to reduce the volume to 1.1 meter cube. So VF is 1.1 meter cube. It becomes. So now the work done you have to calculate. So delta W you have to calculate. Okay. So from the nature of the problem, you already figured out that it's the process is isothermal process, right? So for the isothermal process, you already know the work done is this formula I have to use. Okay, this type of formula I have to use, right? So here it's temperature and nothing is mentioned, but that we can calculate, right? So here PV is some constant K. Okay, here it's already I've written. PV is some constant K. So this K thing you can calculate by putting this initial pressure and volume values. PI into VI. That gives us basically uh, 1.2 into 10 to the power 5 into 2.5. The units are consistent, yes. So it gives you 3 into 10 to the power 5 meter cube Pascal. Okay. Now, so K thing we already calculated. Now, from the expression of this thing, the work done is simply by. So here one important thing is that uh, so we have already calculated, we have already written it. This thing is like, what is that? Yeah. So here is the we are doing some work onto the system. Okay, this is the important thing here. So basically we are pressing the piston right from outside. So basically we are doing some work onto the system. So in this case the work done value should become negative. Okay, so the work done is should be minus of the work of isothermal. Okay, so minus of K into ln Vf by Vi. So minus of K we already calculated, that is 3 into 10 to the power 5. Vf is 1.1 by 2.5. Okay, we substitute the things, we'll be getting as 2.46 into 10 to the power 5 joule. Okay, this is the work done. Okay, next problem, problem 4. Calculate the temperature T of helium after adiabatic compression to 10.0 atm pressure from initial conditions of 1 atm pressure and 300 Kelvin temperature. Assume the gas is ideal. So gas is ideal. Okay. So basically you compress the gas from initial condition, that is 1 atm pressure and 300 Kelvin temperature to 10 atm pressure. Okay, so that means adiabatically. Okay, so you have to find the final temperature. So we know that so since it's a adiabatic process, so it follows. So I for ideal gas we know for the case of adiabatic process it follows this kind of relation. So PV to the power gamma equal to some constant K. So you can write it like this: P1 V1 gamma equal to P2 V2 gamma, right? Uh, Now we can substitute. Yeah, we can substitute PVKT. You can so since this thing is in terms of temperature, you can write the volume in terms of temperature. So V you can write kT by P. Okay. If you substitute this thing here, then this equation will become P1 to the power gamma minus 1 by gamma into T1 equal to P2 gamma minus 1 by gamma into T2. Okay. Also, you can write if in the problem, according to the problem, you can write it in different ways. You can write in terms of pressure temperature, you can write in terms of pressure volume, or you can also write in terms of volume and temperature also. Okay, just by substituting temperature or pressure in terms of temperature and volume. In that case, you get a expression in terms of temperature and volume. Okay. So in different way, you can write this expression depending upon the problem. So in this case, the T final, that is T2, would be P2 by P1, that is gamma minus 1 by gamma. Gamma minus gamma into T1. So helium is a monoatomic gas. I know that. So for monoatomic gas, you know gamma is basically 5 by 3. So we'll substitute this thing here now. So T2 would become 10 by 1, 5 by 3 minus 1 divided by 5 by 3 into T1 is 300. T2 will become, if you calculate this thing, it will give you around 7.5 into 10 to the power 2 Kelvin. Okay. Okay. Next problem is problem 5. Problem 5. For an adiabatic expansion of an ideal gas, the value of delta P by P is equal to half delta V by V, option B, minus gamma delta V by V, option C, minus delta V by V, option D, minus gamma square delta V by V. Okay. So, okay, delta P by P. Okay, so that we have to calculate, or in short, dP by P, that we have to calculate. Okay. So, for adiabatic expansion, so we know for adiabatic case, for adiabatic process, the PV relation holds this form, PV to the power gamma equal to constant K. Now, first we have to do the derivative in both sides. If you do the derivative, total derivative, so in that case, it would become dP into V gamma plus P into gamma V to the power gamma minus 1. The RHS will become 0. Now, you can write dP V gamma equal to minus P gamma V gamma minus 1. Now you can write dP by P equal to, so V gamma will cancel, so it will become uh, gamma minus gamma into, sorry, there is a dV term also there, yeah, dV. So dV by V. V gamma will cancel from both the side. So the option would be this one, minus gamma dV by V. So option B. Okay, problem 6. how much external work mhm, how much external work has to be done to raise the temperature of 1,000 gram of nitrogen from -20 degrees centigrade to 100 degrees centigrade at constant pressure if specific heat at constant volume. So that means CV. CV is equal to 21 joule per mole inverse Kelvin inverse and R as 8.314 mole per joule. Okay, so it's 1,000 grams of nitrogen. So from -20 degree to 100 degree centigrade. Okay. So we know dq equal to du plus dw. So dw is basically dq minus du. Okay. So you can basically directly calculate this thing. Okay. So uh, dw, you know, is already pdv, right? Pdv means p into v2 minus v1, right? So pv2 minus pv1. So this is nothing but R T2 minus R T1. Okay. So R T2 minus T1. So just substitute that. So T2 minus T1 would be 8.314. The difference is 100 minus 20. So it would be 120, right? So just multiply these two things. This gives you around. Okay, so it's mentioned 100 gram of nitrogen. Okay, so 100 grams. So in this case, we also need n also. Okay, so there is n also. Sorry, yeah, because I have to calculate. It's not mentioned 1 mole, right? It's mentioned 100 gram. So I have to calculate n. So n is basically, so nitrogen has molecular volume, so 28 gram. Nitrogen has 1 mole, right? So here 1,000 grams. So it would be 1,000 by 28, right? So 1,000 by 28, you have to put it here. So delta W. So delta W would be 1,000 by 28 into 8.314 into 120. Now, so delta W will become, to calculate it, it will give you 35.63 kilojoule. Okay, not joule, in kilojoule. Okay, okay, so this is one problem. Last problem, problem number 7. And ideal monoatomic gas and a diatomic gas is adiabatically expanded from pressure, volume V1 V1 to V2 V2, sorry, PI VI, PI VI to PF VF. Okay. Find out the ratio of work done between mono and atom. So find the ratio of work done between mono and diatomic gas. So option A is 0.8, option B is 0.6, option C is 0.2, and option D is 1. So the work done is expression looks like Pi Vi. We know it's a adiabatic process we have already discussed. The work done expression looks like this: Pi Vi minus Pf Vf by gamma minus 1. So we know for so gamma is for monoatomic case, this adiabatic exponent we know is Cp by Cv. So for monoatomic case we know gamma mono is 5 by 3, and for diatomic case we know it's basically 7 by 5. That is, we have previously calculated from the degrees of freedom and calculating for degrees of freedom for both monoatomic and diatomic gas, right? Now, if you do the ratio of their work done, so W mono by W dia would be gamma dia minus 1 by gamma mono minus 1, right? So this will give you 5 by 3 minus, sorry, 7, 7 by 5 minus 1 divided by 5 by 3 minus 1. And if you calculate this, it will give you value around 0.6. Okay. So the option is correct option is option B. Okay. So this was the last problem for today's class. So if you have any question, you can ask.
No questions. Thank you so much for the session.
Okay, okay. Okay, so thank you. So I'll now end the class. Okay.